months, they're like pulling the calendar pages. You know, this is the story, right? Okay, you don't have to wait that long. They wait in June, same thing, rotated 90 degrees, no shift. So now either ether doesn't exist, or all of the ether in the universe orbits the sun with the Earth. Yeah? Now, by the way, somebody did, there's two explanations that the people proposed, okay, to explain the non-shift, the non-detection of ether. The first one was just based on fluid mechanics, is that if you actually do have a solid object like the Earth moving through a fluid, right, like golf balls, for example, drag a little bit of the air with them. So the boundary layer next to the golf ball is actually not moving that fast with respect to the golf ball. Right? There's a part of it that's like dragged along with, this is called the ether drift theory, right? Okay, and so the idea is that the Earth is dragging a little boundary layer of ether with it as it goes, right? Yeah. And then the other explanation was that motion through the ether actually causes matter to contract in the direction you're moving. Strangely enough, by the way, not because of ether, this is true. That objects moving will contract in the direction they move, but not because of the existence of ether, which is kind of an interesting thing. So anyway, we didn't detect ether. Like, tried it in June. Right, so basically everybody was so sure that ether existed, they tried to look for it, right? And still we tried to cling to the notion that ether existed, but, you know, let's think of it another way, right? What does light travel through? Crazy, right? So Einstein is now a patent clerk. He's studied physics, and he's I believe he's a patent clerk at this time, right? And we need to think about like what an electromagnetic wave is, right? So concept zero for an electromagnetic wave is that electric fields and magnetic fields contain energy. Yes. If you switch an electric motor off, suddenly, you get a big spark. Have you ever noticed that? Have you ever turned electric motors on or off? Or have you ever unplugged your vacuum cleaner when it's running? Yeah, you could try that. You get a big spark, don't you? That's because the magnetic field that is in the motor that makes it run suddenly collapses, and all that energy turns into a very high voltage spark. And that's because you're changing the flux very rapidly in there, right? But the energy to make that spark comes from the energy stored in that magnetic field. So if I have the poles of a magnet here, north pole on top facing down, south pole on the bottom facing up, and I take that magnet away, the magnetic field that was there contains energy. It can't just go away, but it has to collapse because there's no magnets there to make it, yes? Must have magnets to have magnetic field, or a current carrying wire, something like that, right? And so the magnetic field collapses. Well, guess where that energy goes? It turns into a electric field at right angles to it. This is one of Maxwell's laws, right? Okay, the electric field goes right this, and I picture it sort of like Wile E. Coyote. He runs off the cliff, and there's no cliff to support him, right? Yeah. Electric field looks around and goes, hey, there's no balloons that have been recently rubbed on hair. You know, Van de Graaff generators, no charge distribution here, right? The electric field collapses. A collapsing electric field creates a magnetic field. Creates a yes. Hungry alligator. Sorry. Okay. Where are we? I don't know. He does. Yeah. Here we have it. Right. So that's sort of that's how this is the notion of how electromagnetic waves travel through space, right? So Einstein's sitting there thinking, you know, he's sitting on the meadows in Switzerland, right? Isn't he in Switzerland? I believe he is, right? A Swiss patent clerk, right? And I believe that means he's in Switzerland, right? So he's sitting in these mountains, and instead of singing, you know, the hills are alive, he just starts thinking about this wave, right? Okay, and he starts to think, okay, if I start to catch up, let's suppose I could catch up to a wave. Yes. Oh yeah, yeah. They spread out, you know. Yeah. If they're photons, they just sort of. Say it again. Oh, they eventually dissipate and just, you know. The photons from the Big Bang are still around. They're just so low energy. You need like in microwave stuff to detect it, right? So anyway, what he said was, okay, let's suppose we catch up to an electromagnetic wave. We start running faster and faster. First we run half the speed of light. right? Now the waves are only moving away from us at half the speed of light. Now then we go 3/4 of the speed of light. The wave is shining this way, right? And now the waves are only moving away from us at 1/4 the speed of light. Suddenly we go 9/10 the speed of light. Now they're only moving away from us at 1/10 the speed of light. Now we go the speed of light. We're going the speed of light. We're running along with this wave, right? What does that wave look like as I move the speed of light? Is it moving with respect to me? No, answer quickly or I'll walk into the wall. Okay. No, it's not moving with respect to me. So what do I see when I look at this wave? Imagining that I have like little probes and I can go into space and detect magnetic fields. What do I see? Do I see stationary magnetic fields? Yes, I do. I can just say, hey, look at that. There's a magnetic field there. Now, here's a puzzling thing. What is making these stationary magnetic fields? Well, if it's moving, we have an explanation for this. Maxwell's laws say that a changing magnetic field creates an electric field. A changing electric field creates a magnetic field. We have no problem with that, right? But now suddenly I'm moving along at the speed of light. And I see this magnetic field sitting there absolutely still and nothing is creating it. Haven't the laws of physics suddenly changed? Yes. Now we are in a universe where we can have magnetic fields sitting still for absolutely no reason. Yes? Ah, there's a magnetic field over there. It's always been there. Over there's an electric field. Yeah? Yeah, yeah? So either you have to change the laws of physics if you're moving the speed of light, or you can never go the speed of light. You can never catch up to an electromagnetic wave. Which of these is more palatable? A new set of physical laws that we all have to derive and discover every time we move, or that you can never catch up to light? Yeah, we can never catch up to light. Yeah, that's the thing, right? Okay, you cannot. Light, when it is observed, is always going to be observed traveling the speed of light with respect to us. No matter how fast we're going, we'll always see light traveling the speed of light with respect to us. Okay? So if I'm going this way, and by the way, there's problems with this. This bends our minds in other ways, right? But it turns out that this is supported by experimental evidence, right? Okay, so if I'm in a car, and I'm going 0.9 the speed of light this way, right? Okay, if I'm going 0.9 the speed of light that way, and I turn my headlights on, right? I see the photons from that headlight beam traveling away from me at the speed of light. No, I see them traveling at exactly the speed of light. Yeah?
Well, what is it actually traveling at?
Well, it depends on what frame of reference you're in, right? Now, okay, the light, though, always will be seen going the speed of light. So if this person sees this beam of light, they also see it approaching them at the speed of light, right? And this is sort of weird. Isn't that weird? Yeah? Okay. Now, what's really going on, the way you can reconcile these two experiences, the driver going 9/10 the speed of light and seeing the light traveling away from them at the speed of light, don't you need more space somehow? Yeah? You need like one of those Harry Potter tents where it's like, looks small on the outside, but it's really big on the inside, right? Okay, what happens is, and this isn't going to really help you either, but this frame of reference, this entire frame of reference has shrunk, kind of like one of those Harry Potter tents. Okay, to us it's small, to them it's big. Okay, from inside the frame it's big, but this is called length contraction, right? This reconciles it all. That makes it all clear. Doesn't it? You guys see, I can see the smoke coming out of your heads, right? Okay, don't worry, we'll make it all clear with this other bizarre notion, right? Okay, so yeah, this person's going to see that light at the speed of light. Now, by the way, we can relate this to some of your experience, right? What's going to be the Doppler shift on that? If that light was originally white light, it's now going to be approaching as shorter or longer wavelength? Shorter wavelength. Yeah, there we go, right? So basically the wave has shrunk along with its frame of reference, right? Yeah, yeah? Isn't that weird? That's sort of weird, right? That means the people shrank, the car shrank. The car, in the direction it's moving, it shrinks like this, right? That's where we're headed, right? So this person sees that light traveling at the speed of light, right? They see this person going 90% as fast as that, yeah? So in this person's frame of reference, they see the difference in velocity between this guy and the light as 1/10 of the speed of light. The person in the car, of course, sees it as the full speed of light. This is a crazy thing, right? So that's kind of weird too, isn't that weird? That leads to all sorts of things like time not traveling at the same rate, length not being the same, measured in different dimensions, right? But once you do all that, everything else works. Yeah?
source